But what better way than you learning more about me, because you'll be hearing me most of this afternoon, than to hear a bit about my research in terms of more recent activities. What I'll do is I'll give you a brief overview, particularly trying to elucidate some of the role that I think machine learning has to play in design for AM. I will follow this curve of progression, where the first part would be trying to answer the question how we can accelerate support-free design with current capability. Next, I would like to delve into how we derive machine learning informed lattices in the near future timeframe. And lastly, looking ahead, how we can tease out how design optimization for multifunctionality will help us progress both DfAM tools and AM in general. This is just a very quick refresher slide. Those who are familiar with the traditional SIMP method would notice the equations on the left. Those who have seen the practical implications of this will see the solution on the top right. Bottom line is we want structures like the beam showed in the color green, which are more stiff and more typical topology optimization problems. And we want to avoid the ones which look like the red beam, which deflect a lot more. Great, so let's delve into the first area. Many of you would be familiar with this. Supports are inevitable part in manufacturing when it comes to AM in several processes. A lot of them is arising from the violations in overhang angle, and in metal AM quite often due to the inadequate anchoring support or poor heat transfer present. Ideally, we want to avoid support structures because they require post-processing, and also sometimes removal of these can result in part failure. They generally have poor finish as well. More importantly, what has been shown by one of the earlier works by Larry in this nice case study is there is usually a penalty both in terms of time and material when introducing supports. On the table on your right, you will see that if we use supports, a lot of our entries are in red colored, which indicate higher consumption of material and higher time requirement to make that support structure possible. Whereas if we go towards the support-free topology optimization design, which is the last row in our section, it gives us a good solid solution, has minimal excess time requirement and material utilization requirement needed. So building upon from that case study, the illustration on the right-hand side, which was one of the leading works done by Langelar, had shown the community how an AM filter, which is a manufacturing consideration for overhang angle that can be introduced within topology optimization framework, could be used to reveal manufacturer-ready topology optimization paths. In principle, this is an excellent method. However, it comes at a huge computational cost compared to the traditional topology optimization only processes. And therefore, one of our works is building up on this particular approach, but trying to make it more feasible in terms of the computational effort needed. So here I'd like to briefly introduce you what we have attempted in doing here. So the black box indicates the input conditions. So these are what we would like the initial geometry to look like, loads, boundary conditions of our problem, so on and so forth. The box just next to it in gray is the baseline solution that we get from Langelar's method. So this is the one which is computationally expensive. And then we work through the purple colored boxes, which effectively tell us something about the field of this physical field information about this problem. This could include things like stress information, strain energy plots. We run it through our machine learning trained model and hope to get a sensible result out, which is the one you see at the bottom. The illustration on the top right is indicating the method that we have used, which is GANs, or Generative Adversarial Network. Primarily, it's two-part. One is a generator whose job is to create from fake input something that looks like realistic images. And the role of the discriminator is to find difference between the image supplied by generator and the true solution. These became very popular mid last decade when we started hearing about deepfakes. We use an advanced version of this, which is called conditional deep convolutional GANs. I'm not going to go into the details of that, but this allows us to work with higher accuracy and less data required by the traditional GANs method that I just discussed with you. pretty obvious. The quality of the trained model is determined by the quality of the training data. And therefore, we went a very long way trying to have several different boundary conditions, several different design domains, several different load cases, and even introduce different volume fractions for the training set that we used for the results I'm going to present to you. So in this table, you can see in the row colored blue, we have different aspect ratios that have been used. Now, as far as I know, there are very limited studies which have used machine learning for different aspect ratios. The light and the dark yellows indicate the expected and the resultant volume fractions that we want from the final part. So effectively how much the part should weigh. And the result in green indicate the compliance value. A lower compliance value is a better value. So summarizing from that slide, what we have been able to demonstrate is a 20 times faster computation compared to the current best method that we have, which is topology optimization with AM filter with very little compromise on accuracy. We saw compliance value only strained by about 3%, which is before before post-processing, which means we can improve on this. And likewise, our violation for the manufacturing readiness was less than 5%, again, before post-processing, so this could be quite easily rectified. Now, I would like to just mention that we are working towards a more online learning environment, similar to the ones that you get in CAPTCHA inference when you log in a web page, etc., where this trained model would not only be able to design new parts for you, but also rectify any changes or issues to make it manufacturing ready for an already designed part with a minimal change to the original geometry or topology provided. All right, so let's have a look at what can be expected for machine learning informed lattices. Lattices have already found great utility in areas particularly relating to high strength to weight ratio applications and where robustness are needed. Our work is a two-part study. First part is focusing on finding optimal elasticity tensor properties. What we do here, unlike most simplified approaches where generally final element density is used to do some form of mapping of lattices, we also take the end result of a low resolution topology optimization result. We obtain the stress state for every given element, and we minimize the strain energy for an element subject to this elasticity tensor. And then the second part is the one that relates to the machine learning. Here we use an inverse generator, which uses the tensor that we had to obtain what would be the best unit cell topology or geometry in that particular element. Here you can see what the cell parameters reveal in terms of the final geometry. And following the last row of images that we have, you can see how the initial elasticity tensor D, which we would like to attain, which is coming from our optimization procedure, gets a good fit for the cell parameters, which is the middle image. And the accuracy of this is validated with the animation on the right, where we can see a line at nearly 45 degrees, indicating an excellent correlation with predicted and target values for our intended D tensor. Anyways, coming to results. What I've done here is have shaded in a light color where the results are coming from simple density mapping, and a darker color where the results are coming from our machine learning mapping. And we have three cases out here. Case 1, which is using a BCC type lattice. Case 2, which is using an elliptical cutout lattice. And case 3, which is a combination of two different types of cell lattice. And what we can see here is in every case, the compliance value, which lower is better, is indeed achieved with the machine learning solution. Then we also wanted to look at the robustness of this. What we found was by cutting time nearly 40 times, we could get about 5 to 6% higher solution than the best high resolution topology optimization result possible. And this is when we consider variability in the load vector, which means both the magnitude as well as the direction of those load vectors are changing. So in summary, we see marginal improvement over the traditional density-based mapping, but importantly, 40 times higher or faster computation with higher robustness compared to even the best TO-only solutions. This illustration on the right tells us what we can expect from 3D solutions. And just last few slides to tease out what multifunctional design optimization may offer computational tools, especially for DfAM. So I've been fortunate working with some chemists, chemical engineers for the last few years on this topic. And the topic has been broadly split into structural supercapacitor and next generation battery electrodes. What we have found in nature is usually one of the two criteria is fulfilled. Let's say one is structural and another is functional. With some of the earlier work that we have done, we have shown that doing a multi-objective topology optimization in its traditional sense offered significant improvements for what the chemists were looking for. However, these are not necessarily manufacturer-ready solutions, and you have to post-process them. Important thing to highlight is how this is of great benefit to other disciplines. On the extreme top left, you see one of the grayscale solutions just effectively shown to you in 2D. If we focus on the first set of images on the top, you can see how this can be used within a sandwich composite structure where we have the structured polymer electrolyte serving the needs for high ion transport, energy storage, energy harvestation, etc. We did some prototyping in terms of 3D printing some of these microstructures, testing them both numerically and experimentally. And to our surprise, our work, which was based on a more traditional TO-based approach, easily surpassed anything that was known in the battery world by a huge margin. These are log-log plots. And you can see our dashed red curve is very close to what we consider as the theoretical bound. So in conclusion, what I want to wrap from here is requirements and needs from other fields like the one I've just shown you may help shine the light not only on AM, but also help tease out what the role of DfAM is. For example, creating support-free microstructures, which wasn't done in the previous work. And also can help unlock potential for these emerging areas when combined with machine learning examples like the one I've shown to you previously, help us solve large societal problems. One topic that we are looking ahead is using low resolution macro scale modeling to then map micro scale lattices in there. And just like the examples you have seen before where we have used GANs, you can quite readily start to piece all the puzzle together based on the three topics I've shown you of how DfAM and more importantly computational methods can help us achieve this. Lastly, I'd like to thank you for your attention and also just give a shout out to Amber, Bohan, and Shanhui, whose work I had very kindly presented here. I will go in terms of in my moderation mode now. So if there is perhaps one question, I'd be happy to take. Otherwise, I think I'd like to kind of move on with our next presenter. Feel free to add any questions you have in the chat, which we'll be very happy to come back to you. Can I check if anyone had any burning questions they wanted to raise? Okay. With that, perhaps for the sake of time as well,